This speech is my recital. I think it's very vital to rock
around.
That's right.
On time.
It's tricky. It's the tight.
Here we go. It's tricky to rock around. To rock around. That's right. On time. It's tricky. It's tricky. 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 It's tricky to rock around. To rock around. That's right. On time. It's tricky.
Okay, continuing on with the wonderfully challenging 4.4 applied maximum and minimum problems. Remember that the short form for this is optimization. If you hear the words optimization when you're doing calculus, these are the sorts of questions you're doing. So without further ado, let's get right to it. If 2,700 centimeters squared of material is available to make a box with a square base and open top, find the largest possible volume of the box. So you remember that the first thing we want to do is we want to draw a picture. So what we have is a box, and there is no top on this box. Not really sure how to draw that, but there's no top. It's open. Okay, and what else? What we want to do next is we want to write an objective function. What is the thing that we're trying to optimize here? What we want to get as big as possible is the volume of this. So our objective function is going to be volume equals volume of this. What you do is you'd go length times width times height. And our next step is we want to get this down to only one variable. Right now we have 3 variables. We have to get it down to 1. Well, one thing to notice is we have a square base. So we could call the distance of the base here, we could call this x. And since it's a square, this could also be x, right? These are the same size as each other, same distance as each other. So that's good. We can already make this volume equals x times h. Or if you want, notice I'm doing way more steps than you need to, but I'm down to this. Okay, but again, I have 2 variables, I only want 1. There should be some other information in here I can use, and indeed there is. It says if 2,700 centimeters squared of material is available. So when they're talking about the amount of material available, we're not talking about volume, we're talking about surface area. So this is going to help us to get this down to only 1 variable. We're going to write down some information about the surface area. First of all, what's the surface area equal? Well, let's call this h. And in order to get the surface area, what you would do is you would get the area of the bottom face. So that'd be x times x, or x squared. And there's only one of those. Not going to multiply by 2 because the top isn't open. And then you get the area of one of these faces right here, which is x times h. And how many of those are there? There's 4 of them. 1, 2, 3, 4. So we're going to add on to this 4xh. And we actually know how much the surface area is. The surface area is 2,700. So we have 2,700 equals x squared plus 4xh. Now, which one of those 2 variables, the x or the h, would be easier to isolate? By far, it would be easier to isolate the h. So let's do that right now. We're going to move the x squared over. We get 2,700 minus x squared equals 4xh. And we're going to divide both sides by 4x. So you get 2,700 minus x squared over 4x equals h. This is great because now what we can do is rewrite this, our objective function, but instead of putting h, we can write 2,700 minus x squared all over 4x. We're almost ready to take the derivative. Let's just simplify a bit here. So we've got 1x here and 1 there. Well, actually we got 2 here, but we're going to get rid of 1 and this x here. So what we're going to have is x times 2,700 is 2,700x minus x times x squared is x cubed all over 4. And just to make it a little bit easier for us, we can take the derivative of this, but I think it might be easier if we actually divide both of these terms by 4. So 2,700 divided by 4 is 675. So we have 675x minus 1 over 4 x cubed. This is our objective function with only 1 variable, and that's what we want. Next thing we want to do is we want to figure out what the domain is. So the domain is, we're referring to the x's here. How big or how small can the x's be? Well, if you think about it, we're talking about the lengths of sides. The domain has to be bigger than 0, right? Can't be a negative amount. Can't be 0. As to how big it is, we could probably figure something out about that, but I think that's enough for us just to say that. we're just going to say that x has to be greater than 0. Okay, that said, we're now able to take the derivative. So v prime equals, so the derivative of 675x is 675 minus, okay, power rule says the 3 comes down and multiplies the quarter, so you get 3/4 x, and then the 3 drops down to 2. And what I've been kind of training you to do is always to get a common denominator when you do this. It's more important when you have like a variable in the bottom, an x or an x squared, but what the heck, we can still do it. Not necessary, but let's do it. Put this over 1. So what we have to get a common denominator 4. So we have to multiply top and bottom by 4 here, which gets us back up to 2700 minus 3x squared. And let's factor on the top as well. What can you take out of both of those? Take out a 3. So you get 3, and then we have 900 minus x squared all over 4. And you can factor the bracketed part here as well. It's a difference of squares. So I think this will be our last step for the derivative. V prime equals 3, 30 minus x, 30 plus x, all over 4. And it's time to get our critical numbers. So to get our critical numbers, the first thing we want to do is look at when does this derivative not exist? Well, it always exists, right? Because you'd ask yourself, what would make the denominator equal 0? Nothing makes the denominator equal 0, so we're good. The second thing we need to look at is when would the numerator equal 0? Or when would the whole derivative equal 0? But in order for the whole derivative to equal 0, the numerator would have to equal 0. So we're wondering, when does 3 times 30 minus x times 30 plus x, when does that equal 0? Well, you can ignore the 3 because you can just divide both sides by 3. Hey, it's already in factored form. You get two answers. X equals 30, x equals negative 30. Okay, but hey, we already set up here in the domain, x has to be greater than 0. So we can reject this right here. Doesn't make sense. You can't have a negative 30 as the distance, the side length of your box. So we have one number to put on our wiggle graph, which is 30. But hey, we said the smallest you can possibly have. The domain tells us the smallest you can have is 0. So let's also put that in there. And then we do not need to worry about this, of course, because you can't have any lengths that are less than 0. So we have two intervals to check here. Where are we going to check them? We're going to check them right here. You know 3 is positive, you know 4 is positive. You don't really need to worry about those either. You just need to actually worry about this bit right here. So let's try something in this interval. I'll try 10. 30 minus 10, that's positive. 30 plus 10, that's positive. Positive times positive equals positive. So our function is increasing here. Let's pick something bigger than 30. I'll pick 100. 30 minus 100, negative. 30 plus 100, positive. Negative times positive, negative. This is decreasing. If something's increasing and then decreasing, we get a maximum. So 30 is our maximum. Is that what we wanted? Did we want a maximum? Way back up here. Yes, largest possible volume. So this is not, 30 is not the largest possible volume. That's when you get the largest possible volume. We still need to figure out what the largest possible volume is. Well, obviously this is 30 and this is 30. We just need to figure out what h is. So you could do that by plugging 30 into this, or the other thing you can do, and I think I'm going to do this, is you could get the volume just by plugging into here, put your 30 there and your 30 there. So I think that's probably the best way for us to do that. The volume is equal to 675 times x, and we found that x is 30, minus 1/4 times 30 cubed. So this equals 20,250 minus 1/4 of 27,000, which is 20,250 minus 6,750. And if you subtract that, you'll get 13,500. So our maximum volume for this is 13,500, what are we talking about here? Centimeters. 13,500 centimeters cubed is our maximum volume when we're constrained with 2,700 centimeters squared of material. Okay, we did it. Okay, a cable television company is laying cable in an area with underground utilities. two subdivisions are located on opposite sides of Willow Creek, which is 100 meters wide. So let's start by drawing that. We have, here's a bank and a bank, right? I got, and it's 100 meters wide. So from here to here, it's 100 meters. The company has to connect points P and Q with cable. So I'm going to call this point right here point P, and Q is 1200 meters east of P. They're on opposite sides of the Willow Creek. So 1200 meters down is point Q. So this distance from here to here is 1200. It costs $40 per meter to lay cable underground and $80 per meter to lay cable underwater. What's the least expensive way to lay the cable? Okay, now you might think it's better to go down underground to here and then straight across under the water because it's cheaper to go underground. So shorten this distance underwater. You might be right, but it also might be wrong, because if you have to take a strategy of stopping somewhere around here, like going underground to about here and then underwater to there, yeah, you have a little bit more underwater, which is expensive, but you also have a lot less on underground, so it could work out being better. So we have to figure out what's that optimal point where we go from underground to underwater. I'm going to call that point S. So how we're going to do this is we're going to lay some wire, some cable underground from here to here. Now whatever that distance is, I'm going to call it X. And then we're going to lay some more cable underwater from here to here. And what I'd like to do is I'd like to figure out, well, what am I going to call that distance? So any ideas how you're going to figure out that distance? You're going to draw a line right here. So you end up with a lovely right triangle. Now you know how much this is. This is exactly the same as this. This is 100. And you actually can write an expression for this. See how this whole distance from here to here is 1200? That means from here to here is also 1200, which means from here to here is not 1200. How much less is it than 1200? You got to take x away. So this is 1200 minus x. Now you're going to use Pythagorean theorem to write an expression for the length of the hypotenuse here. Okay, so we have two things. We have the cable underground here, and what we're interested in is the cost underground. And the cost underground is $40 per meter. And how many meters do we have here? X meters. So 40 times X. That's the cost underground. That's easy. Like an easy expression to write. Not so easy for the cost under the water. Because how much does it cost there? It costs $80 per meter. So it's going to be 80 times whatever this is. What's this going to be? Well, it's going to be this squared plus this squared equals that squared. Or in other words, it's going to be the square root of this squared plus that squared. So it's going to be the square root of 100 squared plus 1200 minus x squared. This bit here, if this confuses you, this bit here is the Pythagorean theorem statement to figure out that hypotenuse right there. Okay, great. So then the total cost, which is what we want to minimize, right? We want the least expensive way. So this is our objective function. What we're trying to minimize is going to be the cost underground, which is 40x, plus the cost above ground, which is 80 times the square root of 100 squared plus 1200 minus x all squared. And now we need to make sure we only have one variable over here. And we do. We have x, and that's it. Great. Wow, isn't this easy? No, wait till you see the derivative and all the simplifying you have to do. It's actually quite amazing. But before we do that, let's figure out the domain. So we're talking about x, which is this length here. Well, since we're talking about lengths, we know that x has to be more than 0. But what's the most x can be? It could stretch, because remember, s doesn't actually go there. We don't know where it goes. It could go here, 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 here. What's the furthest it could go? Well, it could go all the way up here, couldn't it? We don't know yet what the optimal is. So what if it went all the way to there? That's obviously the most it's going to go. You're not going to go past and then back. That wouldn't make any sense to go past that point and then come back underwater. So this is the biggest point right here. How far is that from P? 1200. So our domain is from 0 less than x. Could it be 0, by the way? Sure, it could be 0. Maybe the cheapest is just to go straight underwater. I don't think so, but maybe it could be just straight underwater. So less than or equal to x, and then less than or equal to 1200. Awesome, we're ready to take our derivative. You ready for this? It's pretty crazy. C prime equals, okay, the derivative of 40x, 40. Hey, easy. This part, not so easy. Remember, what we have here is the square root of all this. So what you might want to do, maybe I should have done this already, is rewrite this. You can write another line below if you want, but I'm trying to save some space and time. Since it's the square root of all this, it's all this to the 1/2. So you're going to have to use some chain rule here. In fact, I think you're going to use multiple chain rule. So our outer function, we have 80 times something to the 1/2 power. So we have to deal with that first. The 1/2 comes down and multiplies by 80, so we get 40. And then the something, the inside part here, stays exactly the same. All of this mess here stays exactly the same. But now it's not going to be 1/2, it's going to be one lower than that, which is negative 1/2. And we have to multiply that by the inner function. So when we look at the inner function, what we're looking at now is this, all of this. So we got to get the derivative of that. We're multiplying, remember. So the derivative of 100 squared, well, that's just a constant, so that's 0. And then we have 1200 minus x all squared. Chain rule again. We have something squared. So the 2 is going to come down, multiplied by the 1200 minus x, and then that 2 is going to drop down to a 1, which you actually don't even need to write. And then you have to multiply that by the derivative of the inner function. So the derivative of 1200 minus x. Well, the derivative of 1200 is 0, and the derivative of negative x is negative 1. Wow. Okay, let's simplify. We'll keep the 40 here. Now, in the top, we have a 40. This is multiplied. All of this is being multiplied, and we're also multiplying by negative 1. So we can multiply 40 and 2 and negative 1 and get negative 80. So we have negative 80. We also have this 1200 minus x on the top. And then all this 100 squared plus 1200 minus x squared, all to the negative 1/2. That's a flippin' negative. It's all going to come to the denominator. And since it's going to be the 1/2, that means the square root of 100 squared plus 1200 minus x all squared. So I told you this is crazy. What we're going to do next is we're going to get common denominators. So we have to multiply top and bottom of this one by all this denominator. So we get c prime equals 40 times 100 squared plus 1200 minus x all squared minus 80 times 1200 minus x all over 100 squared plus 1200 minus x squared. And we could factor out a 40 in the numerator here. This really isn't that fun, is it? 40, and what we have left is 100 squared plus 1200 minus x all squared. And then the second term we have 2, 40 times 2 equals 80, and 1200 minus x. And that's still over 100 squared plus 1200 minus x all squared. Okay, we're ready to get our critical numbers. The first thing we have to look at is when does it not exist? The derivative does not exist. Does not exist would be when the bottom here equals 0. But if you look at it, you're squaring this first bit and you're squaring the second bit. So, even if this ends up being a negative part in brackets, if this x is like 2000 or something, and you get a negative 800, when you square it, you get positive. So you get positive plus positive, and then you take the square root of it. It's impossible for this to be 0, right? 100 squared is 10000. This would have to be negative to get it back down to 0, and that's impossible. So this always exists. You don't have to worry about when it doesn't exist. All you need to worry about is when the derivative equals 0. When's the derivative going to equal 0? When the numerator equals 0. So you got to figure out when does 40 times the square root of 100 squared plus 1200 minus x all squared minus 2 times 1200 minus x, When does that equal 0? Okay, well let's divide both sides by 40, so that's gone. And let's move this second term over to the other side. So we'll have the square root of 100 squared plus 1200 minus x all squared equals, move this over, 2 times 1200 minus x. And now what we want to do is we want to square both sides. Let's square this side and square this side. So when you square this side, the square root sign is just gone. You have 100 squared plus 1200 minus x all squared equals, when you square this side, you're going to square the 2 and get 4, and you also have to square the part in brackets, 1200 minus x squared. And you'll notice I haven't expanded any of this stuff, and there's a reason for that. If you take a look here, you have 1200 minus x squared and 1200 minus x squared. That's great. Let's keep the 100 squared over here, equals 4 times 1200 minus x all squared. Let's move this 1200 minus x all squared over to this side. You get minus 1200 minus x all squared, which means how many of these 1200 minus x's all squared do you have right here? You have one of them. So if you have 4 of those 1200 minus x all squared, take away another one 1200 minus x all squared, you have 3 1200 minus x all squared, and this equals 100 squared. I'm still just going to keep it as 100 squared, and you'll see why in a second. We've got to isolate this x, so let's divide both sides by 3. You get 100 squared divided by 3 equals 1200 minus x all squared. In order to isolate now, you have to take the square root of both sides, and you're going to make it plus minus. Well, this works out nicely because the square root of 100 squared is 100. So we have 100 over, we also take the square root of 3, and it's still plus minus, and what's left on this side is 1200 minus x. We're so close now. Now let's move this x over to the left, so we get x equals 1200. Let's move this over. You know what happens when you move a plus minus to the other side? You get minus plus, which is the same as plus minus. So we get 1200 plus minus 100 over root 3. We've done it, and not a moment too soon. It's so painful, right? Now 100 over root 3 is approximately 58. So if you subtract 58 from 1200, you're going to end up with an answer of 1142, and if you add 58 to 1200, you're going to get 1258. But wait a minute, remember our domain said, where is it? Domain said it had to be between 0 and 1200. That's too big, so we're going to reject this answer right here. So we're ready, after all this, for our wiggle graph. We've got 0 as our smallest possible, we got 1200 as our biggest possible, and we have 1142 here. And we're going to test these. Where are we going to test them? Incredibly, we're going to test them right in here. Now, when you test these, you don't even need to worry about the bottom, right? We already discussed this. This is going to be a positive plus a positive. When you take the square root of a positive, it's going to be a positive. You don't need to worry about the 40. So the part you really need to worry about is this right here. And what I would do is I would take a calculator and just try it. You know, I might put like 10 and put 10 in here. 1200 minus 10 is whatever, square it, add 100 squared, take the square root, blah blah blah. You're going to do all that, and you're going to find that this is negative, and in this region it's positive. So it's decreasing and it's increasing, which means you have a minimum right here. And that's what we wanted. We wanted a minimum. Now there's one other thing which I've neglected to say in the previous examples. Remember at one point when I gave you the steps, I told you should also check the endpoints. So that's something else you should do here. In order to figure out what the least expensive way is to lay the cable, you should actually figure out 3 things. You should figure out what the cost of 1142 is. You should also figure out the cost of 0. And you should figure out the cost of 1200. And whichever one's the smallest is going to be your answer. So where are you going to try those out? You're going to have to put it into here. Remembering that this 1/2, I guess I switched it. I'll switch it back now for you. This is the same as this. And, you know, go ahead and do that. Again, I don't think you want to watch me sit here and plug all this into a calculator. I'll tell you, when you get the cost of 1142, you get an answer of $54,928 when you put 0 in. So remember, 0 would be if you just went straight from point P to point Q, just like that. If you put the cable right there, how much would that cost if it was all underwater like that? It would cost you $96,333. And 1200, that would be if you took the cable along here all the way to this point here and then across. How much would that cost? That would cost 56,000. So this isn't a bad option, but if you want to have the minimum amount, you should actually do the cost when it's 1,142 meters along the bank here. So go 1142 along here and then cut across here underwater. Okay, we made it. Congratulations, and take a deep breath.
And lots of dope, but we just leave it alone. It's like that, y'all. But we don't quit.
You keep on
Rock, shock,
'cause this is it.